Hello there, Mr. B again. This is video number 2 on the revision for EIR. So we're doing revisions on EBN that a couple of you did either a year ago or the mechanical guys have done it 2 years ago. So we need a bit of a refresher. So in this video we're going to cover a couple of topics in chapter 2. Ideal circuit elements, sources, independent, dependent, sign convention, branches, nodes, loops, meshes, series and parallel, ohms and Kirchhoff's laws. So what I'm going to do is I'm going to run through the theory relatively quickly, and then I want to get to examples that we're also going to do by hand. So let's move on to, I think, ideal circuit elements. There are 3 basic kinds of elements. The first is a resistor. Where's my pen? There we go. The first is a resistor, which we denote by a nice little zigzag, as you should remember. Then we've got capacitors. Remember we spoke about the 2 plates in which the energy is stored in a electrical field. And then there's inductors, that we can circuit element like this, and in which the energy is stored in the form of a magnetic field. Then there's 2 kinds of sources, a voltage source and a current source. When you look at circuit elements in terms of voltage and current sources, so on the left there's 2 different versions of a voltage source. So on the left, far left, we've got a circle voltage source. So that denotes a independent, that's very important, it's an independent voltage source, and the one on the left can be used for a constant or a time varying voltage. The one on the right hand side, this one, that's purely used for a constant DC voltage. Then on the right hand side we have the current source, a little arrow flowing, which indicates the current that will flow. Again, it's a circle. In other words, over here we've got a circle which denotes that it's an independent source. Just like on the voltage, let me just get a different color pen here. Just like the voltage over here, it's a circle that we have. So the circle denotes an independent source. Now what do we mean with independent? Here at the bottom we have an ideal independent source. There you go. An ideal independent source is an active element that provides a specified voltage or current that is completely independent of other circuit elements. In other words, it doesn't matter what happens in the rest of the circuit, there will always be that specific voltage across that voltage source, and the current through that source will always be the specified current. So what do we mean with constant sources? So an ideal voltage source delivers whatever current is required to maintain its voltage. Remember, it's an ideal voltage source. So whatever is needed, it will deliver whatever current to keep its voltage constant. Where an ideal current source will deliver whatever voltage is required to maintain its current. So here at the bottom, for number 9, so for a constant current source, so here we've got I on the vertical axis, we've got volts on the horizontal. So for a constant current, so there we can see the value stays constant for the current, so that's a constant current source, and for the voltage stays constant, irrespective of what the current is doing. So it doesn't matter whether the current goes positive, whether the current goes negative, you always have the voltage stuck at that specific point or value. Then open circuit, short circuit. So this slide might be a little bit confusing. So if we start at the top, so 5-volt voltage source connected to an open circuit, which means that the voltage will be 5 volts and the current will be 0 amps. Why 0 amps? Because current, strictly speaking, can't flow through an open circuit. So what we have over here is a plus, minus, and the source connected to an open circuit. So there's nothing in between. So then the volts will be 5 volts and the current will be 0 amps. If we were to now make a short circuit, in other words, we connect those 2 terminals, then what's going to happen? Then the voltage across this is still going to be 5 volts, but in order for that to happen, then the current that's going to flow through this has to be an infinite value. Right, remember, we're talking about ideal sources. In reality, this can't happen. In the case of a current source, if we have our current source like this, kind of, and we connect that to an open circuit, so now you've got a bit of a problem, because once we're going to say that this is a 5 amp source, 5 amps, so we want 5 amps flowing. That source must always deliver 5 amps, but now there's a short circuit. So what does that open circuit? So that requires that voltage to be an infinite voltage in this case. But what if we do a short circuit, and now we short circuit a different color, that one. So now we put a short circuit across this. What's going to happen now? Now the current can flow freely through the short circuit, and that means that now for a short circuit the voltage drop is going to be 0 volts in the case of a short circuit. So that was independent constant sources. What happens with a dependent source? So that in a dependent source, now we have a what's this, what a kite, shucks, I don't know what you call this in English. Anyway, it's not a circle anymore, it's a kite-shaped source. So what does this mean? This is still a voltage source. How do I know it's a voltage source? Because there's a plus and there's a minus, so it has to be a voltage source. In the case of the current, there's still the little arrow there, so that tells me it's a current source, but it's not independent anymore. It's now a dependent voltage source and a dependent current source. But dependent on what? So an ideal dependent or controlled source is an active element in which the source quantity is controlled by another voltage or current. So for the voltage source, you can have a voltage controlled voltage source. In other words, this voltage, the voltage of this source, is controlled by the voltage of this source is controlled by another voltage in the circuit. Or you can have a current controlled voltage source. In other words, the voltage is controlled or determined by a current somewhere in the circuit. On the current side, we can have exactly the same story. We can have a voltage controlled current source. In other words, the current is controlled by a voltage, or we can have a current controlled current source. In other words, the magnitude of the current is controlled by a current somewhere else in the circuit. Or we'll do a couple of examples of those just now. But here's another circuit illustrating a dependent voltage source. So over here, we know it's a voltage source. Why? Because there's a plus and there's a minus. So we know it's a voltage source. But what type of voltage source? We've got some constant K and then I volts. In other words, some magnitude times a current will give me the volts. So this is a current controlled voltage source. But what current controls this voltage? The current over here is going to determine what the voltage is over there. So for this one, we need to solve this current. If we know what the current value here is, we will know what the voltage is over there. So this is going to require some simultaneous solutions, or more than one equation, to actually solve this circuit. Ideal elements. So for an ideal element in terms of resistors, capacitors and inductors, there's a couple of laws that apply, and actually they're all Ohm's law. So to an ideal resistor, we have the all-important Ohm's law. Volts equals current times the resistance, and that equation you've known since your school days. Then for a capacitor, we have the law, also a voltage-current relationship. So for a resistor, we have this is called a linear a linear relationship. In other words, the current and the voltage is directly proportional in terms of the resistance. For a capacitor, remember the voltage cannot change instantaneously for a capacitor. So the current in a capacitor equals the capacitance times the rate of change of the voltage. So the current equals the rate of change of the voltage times the capacitance. For the inductance, we have the voltage equals the inductance times the time rate of change of the current. Now remember, for inductor, what can't change instantaneously? The current can't change instantaneously. So these two equations look more or less the same, but it's I equals C dV dt, dV dt, because we take the derivative of the parameter that cannot change instantaneously. For a capacitor, the voltage; for the inductor, the current. So for the inductor, it almost looks like Ohm's law, V equals L di dt, but that's a very handy equation that we're still going to use a lot. So this applies to ideal elements. Real world elements, as I already mentioned, is not ideal. So what we have here, there's what we call parasitic elements. For example, a resistor has some parasitic inductance, and it will also have some parasitic capacitance involved. The other thing is that the values of the components will change with temperature, the voltage, the current, or even the frequency. The resistors that you're going to use in your practical, for instance, are called 5% resistors. So that resistance can vary plus minus 5% in terms of what the actual value is, but also as the resistor gets hotter, the resistance goes up. As the temperature cools for a resistor, the resistance will drop. So it can be temperature dependent. Then another thing is that real world sources will not be able to supply infinite power. I mean, there is no such thing as infinite power. Well, from a human perspective, anyway, for us humans, there's no such thing as infinite power. So for example, a 12 volt power supply cannot supply an infinite current at 12 volts. In other words, let's just quickly draw a source again, like this, and if we were to connect our source to a short circuit, you are not going to get infinite current flowing through the short circuit. Well, for one, this wire will probably burn out. Then this voltage source, always there's some small internal, that's a resistor, some small internal resistance, parasitic element in the source. So there's going to be a voltage drop across that internal resistance, which is going to limit the current that can flow. So you cannot have an infinite current. So real world sources, last point, may not provide constant output. For example, a transformer-based power supply may sag when a large current is being drawn, and to mitigate this, a regulator is normally used. So again, what's the principle here? Inside a real transformer, that we're later going to see a transformer as this symbol. Guys, you have to pardon my handwriting. I'm writing I have to look at the screen and write in another place on this page thingy. So hopefully as the slides go on, as the videos go on, my handwriting will get better. Anyway, when the current flows through this transformer, if you were to connect the load on the secondary side of a transformer, then there's again parasitic elements on the inside of the transformer, internal resistances, internal inductances, that actually causes a voltage drop inside the transformer as the current flows through that transformer. So you actually have a voltage sag when across the transformer when it's drawing large currents. Then moving on to the sign convention. Now this is very important that we need to understand. So most of the time, or not most, all of the time, we're going to use what is called the passive sign convention. In other words, current enters the positive terminal of a resistor, and then you have a voltage drop. In other words, when the current goes in one element through an element, that's going to be the positive side, and the negative side is where it goes out. So it doesn't matter what the element looks like. If we first define the potential difference, then we are assuming that the current will flow in that direction for a passive component. Passive component meaning a resistor, inductor, a capacitor. In other words, it needs its energy needs to come from somewhere else. It's just passive. Or on the other hand, if we were to first define the current direction, let's say we choose the current to flow from left to right, then by default we're going to make where the current goes in the positive terminal and where the current comes out the negative terminal. Right, so that's if we use this convention, that gives us positive power. In other words, if you're going to write down power, then we have P equals plus VI. If for okay, we'll do that in the next example. In the next slide, we'll talk a bit more about that. Right, at the bottom we've got the case for active component sign convention, and here the current enters the negative terminal, and that gives us negative power. So as it says, we usually only use the passive sign convention in text to be safe. So I'm going to explain a bit more about the sign convention in the next slide. But let's quickly talk about the passive sign convention. So let's assume for now we have a circuit element. Let's just make the line a bit thicker, that one. So let's draw ourselves a nice big old circuit element. Yeah, right. And now we are going to predefine the voltage. Positive, make that the positive terminal, make this our negative terminal. Now according to the passive sign convention, let's choose a color for this one, blue. Let's see if the blue is going to work. Let's see. According to the passive sign convention, we want the current to go into the positive terminal. That means that we need to write power. We can write power equals, mooi man. Sorry, it needs to be power equals, just get that out there. Right, power equals plus VI. Right, power equals plus VI. Why a plus? Why do we want a plus over there? Because the current is entering the positive terminal. In other words, the current is entering the positive terminal. What would happen if we were to find out, or for some reason we let the current come in at the negative terminal? What do you think is going to happen then? Indeed, P is going to be equal to minus VI. Again, why a minus? Because the current is going into the negative terminal. So that's the passive sign convention, and it's critical. So most of the cases, you're going to either define the polarity first and then the current, but irrespective of what happens in the end, as long as you stick to this convention, in other words, if the current goes in at the positive terminal, it's a positive sign. But if the current goes in at the negative terminal, then it's a negative sign. Branches, nodes, loops, and meshes. Now here usually we just try to not make a mess out of the meshes. So let's see what's going to happen here. Alright, number 9. Doesn't want to, there we go, red pen. Right, so what is a branch? A branch represents a single element such as a voltage source or a resistor. So we're talking about a branch now. Too thick a line. A branch represents a single element such as a voltage source or a resistor. The number of branches in a circuit equals the number of elements in the circuit. So if we look at this circuit at the bottom, there is 1. Oopsie. There's a number element number 2, there is element number 3, there's element number 4, circuit element number 5, circuit element number 6. So we've got 6 branches in this circuit. Right. What happens in terms of nodes? What is a node? A node is a point of connection between 2 or more branches, or in that case 2 or more components in the circuit. So let's count the number of nodes. Now you can already see the answer there at the bottom says there's only 4 nodes. So where does that come from? So between the V1 and R1 we've got a node over there. They're connected. Then on this node we've got R1, R2 and R3 connected. On this node you've got R3, R4 and R5 connected. So this whole bit over here is effectively one big node. Why is it a big node? Because there's no elements in between. And so that's 3 nodes. So let's call this number 1. We'll call this node number 3. This is a big node number 3. Sorry. And then the last one is not just that bit. The last node's not just that, but this whole part at the bottom. That whole section over there is one big node number 4. Why? Because again, you don't have any elements in that section, you don't have any elements in that section, you don't have any elements in that section, so just one big node. So that's what a node is. Right, let's go to what is a loop. A loop is any closed path going through circuit elements. That's one of those trick questions. How many loops do you have in this circuit? So here you see it says 6 loops. You go, where's the 6 loops? Let's do the easy one first. So here we've got one loop. So it's a closed loop. I start at that element's positive terminal. I go around and I end up at the negative terminal. Then I have another loop. So I can go around this loop. It's a closed loop. It means it has to be a closed. The important bit, it has to be a closed path. And then there's a third one sitting over here. So these are 3 inner loops. But then there are also 2 other loops that's a bit more hidden. The one is we can make another loop across those 2. So there's another loop. And then obviously I can also make another loop over there. So that puts us at 5 loops. And then what color will we make the last one? Blue. And then the last loop is the big outside loop, going through all the outer elements. So there we've got 3 red ones, 2 greens, 1 blue, so we've got 6 loops in that circuit. What is a mesh then? A mesh is a loop that has no other loops inside of it. So if you look at the screen at this stage, there's the blue loop, but it has 3 red loops and 2 green loops inside of it, so that's not a mesh. Both of the 2 green loops have 2 red loops inside of it, besides the fact that they're crossing. So the only meshes are the 3 red ones. So those ones, no loops inside the red ones, so the 3 red loops are also called 3 meshes. Moving on to series and parallel resistors. I know you were supposed to or should have done a lot of this in school, but for some reason students keep on struggling with the concept. So let's just look at series resistors first. So series, what does series mean? Series means that the current flowing through all those elements are the same. So when is something in series? When the same current flows through those elements. So in that case, we simply just add them together, R1 plus R2 plus R3. Parallel resistors. When are 2 or more resistors in parallel? They are parallel when you have the same potential. So if we were to measure the voltage across those 2 terminals, then the voltage across R1 plus minus, the voltage across R2 plus minus, and the voltage across R3 plus minus. All three of those voltages has to be the same. Why? Because there at the top they're connected to the same node, and at the bottom all three are also connected to the same node. So that means that they are parallel. How do we calculate the parallel resistance? The safest way is this formula, this one over here. So it doesn't matter how many resistors you have in parallel, it's always 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, etc., etc. The one over here is, I don't want to say wrong, but that's a bit dangerous. So you can memorize that one. But what does come in handy is when you have two resistors in parallel. So perhaps let's do an example on two resistors. I'm going to try and draw it very nice. So it's very handy to know this equation for when you have two resistors in parallel. So what is R equivalent? Man, this writing block is making life difficult. Alright, so what is R equivalent? It has to equal 1 over R1 plus 1 over R2, but we have to take the inverse of the whole thing. So what is this equal to? So in terms of fractions, we know to get to the same answer, I need to multiply the two denominators, and at the top then I can write R2 plus R1, but still we have to take the inverse of this, which gives me the final result of the product of the two resistors divided by the sum of the two resistors. So this equation, where you have two resistors in parallel, this is a very handy equation to use. But whether you use the calculator, whether you use this one and just punch it in 1 over R plus 1 over R and then take the inverse in your calculator, or write it out like at the bottom, completely up to you. Besides, we're not going to see your calculations, we're only going to see your answers on the OCR sheet. So however you want to calculate it, it's completely up to you. But the bottom equation, this one we're going to see, comes in handy when we're going to talk about current division and voltage division. Moving on to Ohm's law. So we've already spoken about Ohm's law, and we always have this joke in electrical engineering that everything in electricity is Ohm's law. And hopefully as we go through the course, I'm going to show you the whole time, see Ohm's law, see Ohm's law. So what do we have? Voltage equals current times resistance, or then obviously we can write current equals voltage divided by resistance. Now lo and behold, for some reason some students still get this wrong. I have no idea how they do that, but V equals IR should be a part of your DNA, even if you're not an electrical engineer. Right, so what does this mean? You have a constant gradient of 1 over R. So here we've got this constant gradient. Not that my hand can go constant, but anyway, you get the idea. So what do we have? This is a linear type of relationship. A capacitor and an inductor, on the other hand, have a non-linear VI relationship. That we'll look at in chapter 7 and chapter 8 when we get there. Moving from Ohm's law to Kirchhoff's laws, and this hopefully will start ringing a bell. So what is Kirchhoff's? There's two Kirchhoff's laws. The one is the current law, and the other one is Kirchhoff's voltage law. What does the current law state? So first, let's just look at Kirchhoff's current law. So here we're looking at the conservation of charge, and it says that the sum of the currents entering a node is equal to the sum of the currents leaving the node. In other words, let's say we decide write in as all the currents are coming in at node number 2, because remember we said that this was node number 1, and then so that one goes in that direction, and then on node number 3 So there the current goes out of that one, and we'll make this current still go up, and let's make that one go out as well. It's arbitrary on how we choose the directions of the currents. So at number 2, what the law effectively says is that all the currents that comes into the node must equal the currents that goes out of the node. So in this case, all the currents are coming in at node 2. I'm just going to write here at the top. So at node number 2, we have all the currents coming in. So let's call this I1. This is going to be I2. This will be I3 according to what the resistors are called. So in this case, we know that I1 plus I2 plus I3 equals 0. All right. Then at node number 3, if you write down Kirchhoff's law at node number 3, all the currents that comes in must equal the currents that goes out. So what are the currents that goes in? There's only one. So here we've got I4. This one we'll call I5 as it goes through resistor 5, and this is still same current as on the other side of the resistor because it's through the same resistor, so it's also I3. So what's the currents coming in? There's I4 is coming in, and that must equal the currents going out. So the currents going out is I3 plus I5. So obviously now you can write it to either side and put your 0 there. So that would mean we can write I0 equals I3 plus I5 minus I4. And if you take everything to the other side of the equation, then all the signs change, obviously. All right. So Kirchhoff's current law, all the currents at the node must add to 0. The other Kirchhoff's law is Kirchhoff's voltage loop law. So here it also works on the basis of conservation of energy, not conservation of charge, as Kirchhoff's current law. So here we've got the sum of all the currents, of all the voltages in a loop is 0. So we can go either clockwise or counterclockwise in any of the loops. So as you remember in a couple of slides back, we could, for this circuit that we're looking at, we could define 6 different loops. So I just want to get rid of this one for a moment because that V is not where I want it, and that one's not where I want it. I want to call, so this one we will call, wrong color. Sorry, it's not wrong color, too thick. So I want to use, let's call this one, it's not going to be too narrow. Okay, we'll call this our source voltage. Then for this one, let's call this one plus minus V1, and we will call this plus minus V3. We will call this voltage drop across this resistor V. Yes, you've guessed it, V5. And let's take another one here, plus minus V2, and lo and behold, the last one plus minus V4. Right, now we need loops. So let's take an easy loop. Let's take this as loop number 1. So this is loop number 1, and then I will take, let's take the outside loop. Let's take a big loop. Outside loop. We can also use that one. So that will be, we'll call this our loop number 2. Right, so if we write down at the top, we write down Kirchhoff's voltage loop law for loop number 1. So we start at the source. Very important, what direction did we choose? Well, I chose clockwise. And now you have to write the polarity in which the loop goes in. So this one goes in at the negative terminal of Vs. So I have to write down minus Vs. Then it goes into the positive terminal of V1. So I'm going to write plus V1, and then it goes through V2, also goes into the positive terminal, so it's plus V2 equals 0. So that's Kirchhoff's voltage loop law for loop number 1. So in any closed loop, all the voltages must add up to 0. Then going to the green loop, or loop for loop number 2, if you write it down for loop number 2, so again it goes into the minus terminal of Vs, then it goes through plus V1, then we're going to go through plus V3, then the loop goes through V5, then it goes at the bottom big loop back to Vs. So that's all the voltages in that loop, and the sum of all those must equal 0. So again, all the voltages in a closed loop, very important, a closed loop must add up to 0. Alternatively, as you can see here at the bottom, sum of voltages, the sum of voltage drops must equal the sum of the voltage rises in a loop. So in this case, we had, let's take another color. So here we had a voltage rise actually, and these were all voltage drops. Vs was a voltage rise, these are voltage drops. So that's Kirchhoff's voltage law, but we'll do a couple of examples later on in the example section. Another very handy circuit analysis tool is that of voltage division. So what we're looking at here in terms of voltage division are two resistors in series. We've got R1 over there and we've got R2. What's very important in this case is that you have the same current flowing through both the resistors. So I1, the current sitting over here, it's the same current that flows through both of the resistors. So if you first write down, I just want to check, if we first write down a voltage or a current equation for the circuit. So I want to calculate what is the current. Let's say we know what the voltage is. So let's say we know what the voltage is, we know what the resistance is, we know what R2 is. So the only unknown in this circuit is the current. So then we can use Ohm's law to say, all right, that means that I must equal V over the total resistance in this case. So what's the total resistance? We have V divided by R1 plus R2. Right, so V equals R1 divided by R2. But so that's using Ohm's law. But we can also say, all right, but we want to know what the voltage is across R1. What is V1 and what is V2? So we want to know what is that voltage, we want to know what is that voltage. So let's write down again Ohm's law. V equals I is the current flowing through the resistor and the resistance is R1. But wait a minute, we know what I is, so let's substitute R1. So this whole term over here, which represents the current, we're going to plug into the place of I. So what do we get? Then we get, in other words, V over R1 plus R2. I must say my handwriting is getting a bit better. Times R1. Oh, that's bad again. So then we just simply reshuffle the equation a little bit and we write R1 over R1 plus R2 times the voltage. So what do we have? How do we know what the V1 is? How do we know what V1 is? V1 is the total voltage multiplied by the ratio of R1 over the sum of the two resistors. So that's what we have here, exactly what we've got at the bottom. And we can obviously then do exactly the same for V2, but now we've got V2. In other words, we need R2 at the top, and at the bottom it's still the sum of the two resistors multiplied by the total voltage. So that's a quick way of calculating what the voltage is across a series combination of resistors. So very important, voltage division works when you have a series combination of resistors. So we've looked at voltage division. Now let's look at current division. As we said, voltage division works for resistors in series. current division works for resistors in parallel, and very important, it only works well for two resistors in parallel at a time. So here we've got two resistors. So what do we know? Let's assume we have the voltage, we know what the resistance is, and we know what that resistor value is. What we want to figure out, we want to get to this equation where we have I1 as a function of the total current, and we want to figure out what I2 is as a function of the total current. So how do we get this relationship between the two? So we know, because it's parallel resistors, we know that the voltage across resistor 1, so the voltage drop across R1 must equal the voltage drop across R2. Why? Because both of them have the same potential across them. They're parallel between nodes A and nodes B. So we can directly calculate I1 simply as the total voltage divided by R1, and similarly we can say I2 equals the voltage divided by R2. Right, but that doesn't give me a relationship of I1 as a function of I. But what is the voltage? We know that voltage equals I R total. So the current is now the total current, R total, and the supply voltage. So this one we have, I1 is, I is one we're looking for, and R total we can calculate. What is R total? R total, we can write, it's a parallel combination, so we know it's R1 parallel to R2. But then we know the shortcut equation, as we've seen a little bit earlier, we can write it as R1, R2, the product, divided by R1 plus R2. So that's the total resistance. In other words, if I now substitute this R total, now I just need a different color. If I substitute this R value for R total into this equation, what does that give me? That then tells me that voltage equals total current times R1, R2 divided by R1 plus R2. Now we're going to substitute this voltage into these two equations, into there, and this also substitute that voltage in there. So let's first write down for I1. What does that then happen? That means that I1 equals 1 over R1, so that's what's left, multiply, now we substitute the voltage, R1, R2 over R1 plus R2 times the total current. What happens? That R1 and that R1 cancels out, and we are left with only R2 over R1 plus R2 times the total current. And that is the relationship that we were looking for in this equation. Now you can do exactly the same for I2, and there you're just going to be left with R1 over here. This is just going to be R1 that's going to be left at the top. So what do we notice over here if we just get rid of all this scribbling? So when I do current division, I take, if I want to know what I1 is, I need to put R2 at the top, multiplied by the total current. If I want to know what I2 is, I need to put R1 at the top and multiply by the current, and then I divide by the sum of the two parallel resistors. Very important, this circuit, remember, R total does not equal R1 plus R2 for this circuit. Why not? because this equation, R1 plus R2, means a series connection. What we have here is a parallel equation. So our total, what does the source see? The source sees two parallel resistors, and the total resistance, combined resistance of those two in parallel, is R1, R2 divided by the sum of R1 plus R2. Before we do a couple of examples, it's still very important that you go through your textbook, just page through your chapter 2 that we just now revised. Look at the examples that we did to just try and jog your memory in terms of the type of examples that's there and the problems that we're going to solve. And then here and there, try the odd number problems. Just see whether you still have the hang of things. The next slide, we're going to look at the procedures that we're going to follow, or a procedure that we follow when solving these type of problems. The basic procedure that we're going to follow when solving a circuit, so there's some unknown voltage, some unknown current somewhere in the circuit that we need to find. We always first try and just use Ohm's law. That's the easiest method. If that's not going to work, if that doesn't directly give us the answer, then we need to simplify the circuit a little bit and maybe combine a few series or parallel resistors and do a process until we have reduced the circuit to a solvable circuit. And then in that process, we can also look at trying to use Kirchhoff's voltage law, Kirchhoff's current laws to solve some other currents. So all of these, current division, voltage division, all of these are tools in your toolbox that we're going to use to find the unknown parameter in a circuit. So in the next couple of slides, we're going to do a few examples that you need to follow. All right, there's two more things. When do I apply Kirchhoff's current law and the voltage law? Kirchhoff's voltage law finds currents, Kirchhoff's current law finds voltages. I know it sounds a bit confusing, but you'll see what we mean. And then for current sources, you apply Kirchhoff's current law. For voltage sources, you can apply Kirchhoff's voltage law. All right, let's go to the examples. Right, in our first example, we're going to solve for voltages 1, 2, and 3. So where are they? Voltages 1, 2, and 3. We've got voltage 1. So here's our first question. Then we also need to find voltage number 2, and we need to find voltage number 3. Right, so we're going to solve this using Kirchhoff's voltage law. So how do we do it? What we're looking for is loops in which there is only one unknown. So let's start with voltage number 1. I'm looking for a loop in which if I write down the loop equation, V1 is the only unknown. So obviously if we look at this loop, that's definitely not going to work. There's 3 unknowns. The other loop that we could use, or the only other loop that V1 is in, is actually this rather bigger loop sitting over there. So in this case, you actually have, let's just check, there's a 40 volts, there's a 50 volts, and there's a 20 volts, and there's only V1. Fantastic. So this one seems that this one could work. So let's solve for V1 if we write it down. First, so very important that we want to look at now is the direction of the loop. So if we keep on going in this direction, we are going into the negative terminal of the 40 volts. We're going to go into the negative terminal of the 50 volts, but we're going into the positive terminal of 20 volts, and we're going into the positive terminal of V1. So what is the equation going to look like? Then it means that we have to write down minus 40, and then we go into the minus 50 plus the 20 volts plus V1 must equal 0. So that closes our loop. So we're interested in only V1, so then we can write it as V1 equals, everything goes to the other side, so we've got 40 plus 50 minus 20, and hopefully you're not going to get your calculator out for this one. We've got 90 minus 20, and we get 70 volts. So that's the answer for V1. So how can we find V2 with only one loop? So for V2, it has only, if we take the top loop, then V2 is the only unknown in that top loop. So we write it down. So where do we start? Let's start with the 30 volts, because we're going to enter the 30 volt positive terminal. So we're going to write down plus 30. Then we go into the negative terminal of V2, and the loop goes into the negative terminal of that 20 volts, and that must all equal 0. In other words, what does V2 then equal? V2 must then equal the 30 volts minus 20, and that's going to equal 10 volts. So there's my next answer that I need. Then the last loop, or the last variable that I want, is number V3. So what loop has only V3 as an unknown? Now you need to think big. So the loop that I'm going to use is actually a big loop that goes around this way, the right outside loop in this direction. So if you write down that loop, so then it's only V3 that we need to know. So start at the 40 volts. Let's write it down here. So we're going into the minus 40. Then the loop goes through the 50, but it enters the minus terminal. So it's minus 50. Then we're going through the plus 30. Then we go through plus V3. And that's all. So that needs to equal 0. So in this case, we have that V3 must equal, all the rest goes to the other side, 40 plus 50 minus 30. So again, it's 90 minus 30, and we have 60 volts. All right, as an answer. All right. Now, just to double check ourselves, we're going to use another loop. Let's just get another color. So let's do this loop, the small loop that goes through all three of those voltages, because if Kirchhoff's voltage loop law holds, all the voltages must still add up to 0. So we're going to use this as our checksum. So we're going to write down the equation for that small loop. Let's just make a break there. So where do we go in? We go in at minus V1. Then we go into the positive terminal of V2, and then we go into the positive terminal of V3. So let's see if this works. What is the value of V1? V1 was 70 volts there at the top, so we have to write minus 70 plus, what was V2? V2 was 10 volts plus, what was V3? V3 ended up as 60 volts. Does that equal 0? Let's see. Minus 70 plus 10 gives me minus 60. So let's just write it down. So minus 60 plus 60. And lo and behold, we have 0. So super fantastic. All our loops balance. And that's just a quick way to check that we actually solved the circuit correctly. In example 2, we want to apply Kirchhoff's current law. So again, we've got a couple of unknown currents that this time we want to solve. So we have I1, that we don't know what that is. We've got I2, we don't know what I2 is. And there's an I3, we don't know what I3 is. And we don't know what I4 is. So those are the 4 currents that we want to solve for. So again, we want to find nodes in this time, because it's now Kirchhoff's current law. So the sum of the currents at any node must add up to 0. So we have a node there, we've got another node over there, we've got a node with 3 elements connected to it, we've got another, don't forget that big node sitting here at the bottom, and we've got another node there. So we've got 1, 2, 3, 4 and 5 nodes for the specific circuit, and we want to solve for the current. So again, we're looking for a node where there's only one unknown. At node number 1, I1 and I2 is coming in, so there's 2 unknowns. Node number 2, we've got 3 amps going out in this direction. There's 7 amps going out in that direction, and I2 going out as well. So there's only one unknown for I2. So we're going to start the whole solution by solving for I2. So we're going to write it out as so all the currents are going out. So what are the currents going out? So it means that I2 is going out, plus we've got 7 amps going out, plus we've got 3 amps going out, and that must all equal 0 amps. So what does this mean? This means that I2 is actually how many amps? Minus 10 amperes. So is that a problem? No, it's not a problem. All that means is that in reality, I2 is not flowing from right to left, it's actually flowing from left to right. But we're not going to change the sign. I2 is now minus 10 amps. Right. Where can we solve for next? So now, do we know what I2 is? So now let's just put on a green one there so that we know. Yes, so now we have I2. So if we have I2, we can actually now solve for I1. So let's go and solve for I1. So if we've got I2, there's one answer. So if you write it down for I1, so we're now at node number 1. So yeah, let's perhaps just write down what node we're at. Now we're going to work at node number 1. So at node number 1, currents coming in must equal the currents going out. So what are the currents coming in? I1 is coming in, plus I2 is coming in, and the current that goes out is the 2 amps. So that must equal 2. So what do we have here? We've got, in this case, these are the currents that's coming in, and this is the one that's going out. Now notice I simply wrote plus I2 over here. In other words, it's still a plus I2. I don't care whether I2 is now minus 10 or plus 10. The math will sort itself out, as we're going to see now. So going back, now we substitute. So now we know that I1 must equal 2 minus I2, which means it's 2 minus 10, because remember I2 is minus 10 amps. So that actually gives me 12 amps for I1. So super fantastic. We now also know what I1 is. What's next? So now I2 goes in, I1 goes in, so there's 2 amps. So let's just perhaps, yeah, so that still holds. Next one we can solve for, it seems, will have to be I4. Because at I4 there's only one on. So now we're going to node number 4. We're going to write this one. Let's just drop this one down. Keep that separate. So at node, let's work at node number 4. Because there's also only one unknown. So again, all the currents coming in must equal the currents going out. What are the currents going in? So right from there at the top, we've got this 2 amps coming into that node. So don't forget about that one. It might look out of sight, but it's still there. So there's 2 amps coming in from the top there. So we have to write what's in. 2 amps is coming in. That must equal all the currents that are going out. What's going out? I4 is going out, plus the 4 amps goes out of that node. So in other words, we've got the 4 amps that's going out there, and I4 is also, I4 is going out of that node. So if we now solve for this, so this means that I4 must equal 2 minus 4, which equals minus 2 amps. So lo and behold, we've got another negative current. So I4 is actually also a negative current, minus 2 amps. But that's not going to deter us. We're not worried about that part. So then the last current that needs to be solved is I3. So let's just check. So now we have I4 as well. So now it's only I3 that we don't know. So now we can choose two different nodes. We can solve for I3 either at node number 5, or we can choose to solve for I3 at node number 3. So I'm going to do both just for illustrative purposes. So if we're going to go to node, let's do node 3 first. Node 3. So what happens there? All the currents coming in must equal the currents going out. So what's coming in? There's 7 amps coming in. Then there's another I4 is coming into that node, and the only current going out of that node is I3. But I4, we already know what I4 is, so we can say 7 plus, what is I4? Plug that one in there, so it's minus 2 must equal I3. So we have I3 equals 5 amps. Right, that's when solving using node 3. What would happen, let's just draw a line here. What would happen if we were to solve for I3 using node 5? Because it must work out obviously on the same answer. So in terms of if we write down for node 5, all the currents coming in must equal the currents going out. What's coming in? Let's start the 4 amps. Let's start on the right hand side. So we've got 4 amps coming in. Alright, 4 amps coming in. Then we've got I3 coming into that node. We have then the 3 amps coming into the node, and I1 is going out, so equals I1. But we know what I1 is. We can simply just plug it in from over there. Then we know what I1 is. So we can rewrite the equation. I3 must equal I1 minus 4 minus 3. So that's going to be equal to 12 minus 4 minus 3, which then is 12 minus 3, 5, 7, and we have, now I've got the final answer in my head already. The answer is 5 amps. So lo and behold, then as one would want, you have these two are exactly the same, so it doesn't matter what loop you use, you still end up at the same answer. In example 3, we're going to combine a couple of circuit analysis techniques to solve for two different variables. The first one that we're going to solve for, that they're looking for, is Vx over here, which is the voltage drop across the 1 ohm resistor. And the second thing that they're looking for over here is the power that is consumed in that 12 ohm resistor, P12. So how are we going to go about solving this circuit? Well, to find, what do you need to find a voltage across the resistor? You're going to need Ohm's law. So we know that Vx is going to equal whatever the current is that flows through the 1 ohm resistor multiplied by the resistance, and the resistance just so happens to be 1 ohms. Alright, so that's going to be the voltage across Vx. But what about the power in the 12 ohm resistor? So here we need to, what do we need to solve for the power in a resistor? Let's start there. So from school, you already know that P equals one of two things, either I squared R, in other words, the current that flows through the resistor. So if you're talking about the current through that resistor, it would be that current. Or we can also calculate it, it also equals V squared over the resistance. So what voltage are we talking about now? Now we're talking about voltage plus minus that voltage drop across the resistor. But now notice something about the 12 ohm and the 8 ohm resistor. So now we see that they're connected to the same node at the top, and they're also connected to the same node at the bottom, and effectively there's a whole bit at the bottom. It's just one big node. So the 8 ohm and the 12 ohm is connected in parallel, which means that the voltage drop across the 8 ohms is the same as the voltage across the 12 ohms. So if we can find the voltage across those two resistors, we can simply use the V squared over R equation to find the power in the 12 ohm resistor. But first, we're going to simplify the circuit to find Vx. How are we going to start? Since for now I don't need any of these circuit components, we are going to simplify that part of the circuit starting from the right and simplifying it as we go inwards. And our first step or order of business then is going to be the two parallel resistors, the 8 ohms and the 12 ohms. So let's start over here. So let's start with, let's start a little bit higher. Yeah, so let's just cut this off. That's where we want to end up with. So what we have, we are going to write 8 is parallel to the 12 ohms. All right, so that's a shorthand of writing 8 parallel with 12. So how do we write it out? We say it's 8 times 12 divided by 8 plus 12. So now we're using that parallel combination shortcut. So what do we have? 8 times 12, it's 80 plus 16 gives me 96, and 8 plus the 12 gives me 20, and that gives me 96 divided by 2 gives me 48 divided by 10, so that should give me 4.8 ohms. Oops, almost wrote volts. 4.8 ohms. So that's for the 8 parallel with the 12. So now we should actually redraw the circuit. And I think when starting out with circuits like these, it's very important that every time you've simplified the circuit, you need to redraw it, and it will come in handy. You'll see it later on. So what does our new circuit look like? We've got a current source there, pardon for the writing. Then there's a resistor down here. Let's just keep it for there. Then there's our 1 ohm resistor that we're actually after. Then we still have the 4 ohms, we still have the 3 ohms, we still have the 3 ohms, then we've got the 1.2, and now the parallel combination is all in one resistor. So this is now 4.8, this is still 1.2, this is still 6, and then over here we still have 3, then here we still have 4, over here we still have the 1 ohm, and here we still have the 2 ohm resistor. So what's our next step? What are we going to simplify next? The next one that I want to simplify, perhaps, let's do this whole combination, but now we're going to be, so now let's keep it from right to left. So let's now look at these two resistors. Alright, so how are they connected? They are connected in series. How do I know? Because if I were to draw a current that flows through them, it's going to be the same current that flows through both of them. So they're connected in series. So I'm going to write, in this case, the 1.2 plus the 4.8. What does that then equal to? Equals 6 ohms. So I'm going to be, I'm going to cheat a little bit, I think, just to save a bit of time, and I'm going to wipe all of this out, and let's combine. Yeah, let's do this. I wish there was a quicker way though. But yeah, you're going to see now where this is going to head to. Perhaps I should have just redrawn the whole thing, but anyway, we're almost there. So let's just get rid of all this red. Alright, and then go back to this line. There we go. So that then gets even simplified further, and we're left with a 6 ohm resistor, which is now the combination of the 1.2 plus the 4.8. What's next? Right, there's nothing else in series with a 6 ohm resistor. Next, I'm going to put my sights on these 3 resistors. So how are they combined? First of all, we've got the 3 and the 6 in parallel. So what do we have? We have that is a 3 parallel with 6 ohms plus a 4 ohms in series. How do I know this? If we look at the 3 and the 6, all of that is one node over there, and at the bottom there's another node. Oh, that's not a nice color. So there's one node, there's one node. So the 3 and the 6 is parallel. Once they're parallel, they're going to be in series with a 4 ohm resistor. So what is that equal to? I have to write it out. So we've got 3 times 6 divided by 3 plus 6, and then plus the 4 ohms. That's going to equal, what's that? 3 times 6 is 18, 3 plus 6 is 9, plus 4, that equals 2 plus 4 equals 6 ohms. So again, we've got another 6 ohms in the circuit. So that's going to reduce even further to 2 6s. So if you're going to redraw the whole thing again, and perhaps we should do that in our next slide. Let's simplify the circuit a little bit in our next slide. We can't go back to the previous slide in this recording. Alright, anyway, so how is this thing going to simplify? We are going to simplify the whole circuit. There's still the source, we still have the 1 ohms, then we still have the 2 ohms sitting here parallel with the source, but now we are left with 6 ohms over there, and we are left with another 6 over there. Right, so we've got 6 there now, we've got 6 in that branch, we still have 1 ohm over there, 2 ohms and 20 amps source still. Almost there. Next thing that we can simplify is now the parallel combination of the 6 and the 6. But for that we are going to go, we've run out of space. No, we're not out of space yet. Let's finish this one as well. So what is 6 parallel with 6? Let's just draw a line there. So what is 6 parallel with 6? And this is a neat little trick that you're going to find out, because what you're going to have now is 6 times 6 divided by the sum of the two, which is 6 plus 6. So what do you have? 6 times 6 is 36 divided by 12, and lo and behold, you get 3 ohms. So this is a nice little trick. The moment that you've got 2 parallel resistors of the same value, the parallel combination is always half of the value. So these 2 reduces to just 3 ohms. But let's take the circuit now over to our next slide. Right, so we ended up with that circuit that you are now seeing. Here's my pen, there we go. And we combined the 2 6s into a 3 ohm resistor. So what we found is that those 2 combined in parallel gave me 3 ohms. So if we redraw the circuit once again, and hopefully now for the last time, we still have the 2 ohms sitting there, we have the 1 ohm over there, and now we have 3 ohms over there. So this is, now that thing's in the way, let's just clear out that 3, because that's now going to get us confused. So here we know it's 1 ohm. Sorry, it's just wrong size pen. So this is 1 ohm. This we know is 3 ohms. Sorry. Alright, I'm back. It was just my wife on the phone. Right, we have the 1 ohms, we've got the 3 ohms, and then we still have the 2 ohms, and sitting over here is our 20 amp source. So what we want to solve, remember, we want to find Vx plus minus, so the current that we're looking for is the current that's flowing through that combination. So now we can, with the 1 and the 3 ohms, how are they connected? It's the same current flowing through them, so we can actually simplify the circuit one step further to find the current if needs be. So we can still draw it like this and then do this current. The 1 and the 3 in series, that will give us a resistance of 4 ohms, and then we've got 2 ohms there, and then we still have the 20 amps. So now we can find the current that flows through the 4 ohms, which is the same current, let's just use a different pen. This is the same current that's flowing through the 1 ohm, which is what I am looking for. So let's do a current division in this case. So what is I4 in this case? But I4 is also the current flowing through I1 that we are looking for. If you look at the previous slide, it is going to be the total current I, which is the 20 ohms, 20 amps, multiplied by, now the trick is what resistance. So we know at the bottom it's going to be the 2 ohms plus the 4 ohms. It's always the sum, but now what resistor comes at the top? We want the current flowing through the 4 ohm resistor. So at the top needs to be the other resistor. So at the top we need to write R2. In other words, what do we have? I1 equals the 20 amps, which is the total current, which is the source, multiplied by 2, divide by 2 plus 4. That gives me a 40, divide by 6, and I'm too tired. That's what's that? That's 2/3, just 0.66666. So it needs to be 6.6 amps. That is what is flowing through that resistor and what I am looking for. Right. Well, not yet actually. That's only the current, but now what am I looking for? I'm actually looking for Vx. So now that I have that, I know that Vx equals 1 ohm times the current of 6.6. So well, that one you don't even need a calculator for. Can you believe it? So we've got 6.6 volts across Vx. Right, so that solves our first question in terms of what is Vx. That now is solved. So now what we need to still figure out is what is the power over here in the 12 ohm resistor. And for that we actually need to go back to our previous circuits, because that is now going to help us in solving the circuit. Right. In our previous slide, or the first slide of example 3, at some point we ended up with this circuit diagram. And now we've solved for the voltage across I1, but what we found in the process is the current that is flowing through I1. So in that case, if we're going to write it, the current that's flowing, the red actually shows quite well. Let's use red. So we know that the current that's flowing through here is 6.6 repetitive amps. That's flowing through that circuit. We also saw that we could combine this parallel combination, which is already encircled in red, as a 6 ohms. But where's the part that we're looking for? Where are we in the big picture? If we go back to the original circuit, what do we know now? We know that the current flowing through there is 6.6 amps. We found out that the parallel combination of these two, let's just go back to Y, or these three resistors was 6 ohms, which is the ones over there. And then we found that the series / parallel combination of these three was also 6 ohms. So there was a 6 and a 6. So this current that we're talking about now, let's perhaps redraw this circuit a bit like that. So I'm going to get rid of this section. Let's just get rid of this and replace that with a 6 ohms, so then we can see a bit more clearly what it is that we want. So if we simplify the circuit back to what we want, so we saw that this section over here was also 6 ohms. So now we can do a current division, because what are we after again? Let's just go back a bit, because I'm thinking way too far ahead. So first of all, I need to figure out is I need to figure out how much current goes through this leg and how much current goes through that leg. And once I have the current through this leg over here, I can again perhaps do a current division, that leg through that leg, to find out the power in the 12 ohm resistor. Right. So first I need to figure out what are these two currents. So that is now on this board, it's the equivalent on this side, the equivalent of that current and those two currents. What are those values? So let's just erase these two so that we know which two currents we are working with. So these are the currents that we're working with now. So that 6.6 has to divide itself between a 6 ohm and a 6 ohm. Now you're welcome to go and do the current division, but if we just use a little bit of logic, if the current has to divide itself between two of the same size resistors, what's it going to be? So in this case, we know that I6 in this case has to be equal to I6, which is going to be 6.6 repetitive divided by 2. Why divide by 2? Because the 6.6 amps is going to divide itself into two currents, half-half, because the resistance is half-half. So what we're going to get there then is 3.3 amps. That's flowing through those two resistors. So what do we know now? Now we know that the current flowing through there is 3.3 amps. So now I've got a choice. We can do a current division again to figure out I8. Let's call that one I8. And this one is I12. And then use I squared R. So let's do that approach first. And then we'll do the voltage approach. So what do I want to calculate now? I want to know what is I12. So I12 has to equal I6 multiplied by the other resistor in the parallel branch, which is the 8 ohms, divided by the sum of the two, 8 plus 12. So what's that going to be? It's going to be 3.3 repetitive multiplied by 8 over 20. And that, I'm going to need my calculator. It's late in the day. My head is tired. 8 divided by 20, 3.33333. I get 1.3. Right. So then we get, where's my pen? 1.3 repetitive amps. Which means from this, I can write that P12 equals I12, the current flowing through that resistor squared, times the 12 ohms. So the 1.333 squared, and then multiplied by 12, and then I get, where's my pen again? I get 21.3. 21.33 watts. Right, so that's the amount of power in that resistor. So that's the one way that we can do it. What's the other way that we can approach it? The other way that we said was we can use P equals, if we want to use P equals V squared over are 12. Right, but what voltage do we need for this? I'm going to use the green. I need then the voltage there plus and minus across the 12 ohm resistor. What is that going to be? Well, earlier on, again, if we just use, if we get rid of this for a moment, the very first circuit that we did, what we found then was that these two resistors in parallel was, can you remember how much? 4.8 ohms. Right, so we know that the 3.3 amps that's flowing over here, which color I'm going to use. So we know that this 3.3 amps is now flowing through the 1.2 ohms, but it's also flowing through the 4.8 ohms. So what is the voltage that we're looking for? The voltage then that we need is V equals 3.3 repetitive multiplied by that resistance, which is 4.8. And let me just grab my calculator here. 4.8 times 3.33333 multiplied, and wow, that's a very nice number actually. It works as 16 volts. All right, which means that we know, so where's that 16 volts? Let's just go back to the picture. So now we know, sitting across this or those two resistors, we have 16 volts. So now we can write P 12 equals 16 squared divided by 12 ohms. And now that better work out to 12 divide, and lo and behold, we get 21.33 watts, irrespective of what way we want it, or whether you use current division or voltage division. Right, that is example 3 in quite some detail, and hopefully that brings back good memories and not bad memories of circuit analysis. In our last example, we're again going to apply a couple of same circuit analysis techniques that we've done up till now, but now it's a little bit different because now we've got a current voltage source on the right, but it's a current controlled voltage source. Current controlled, why? Because there's an IX here, over here, there's an IX, 3 times IX. Where is IX? Oh, here is IX is sitting over there. So that means that this current is controlling that voltage. Whatever that current is over there, that is going to dictate what that voltage is over there. So we need to calculate two things. The one that we need to find, one thing, is the voltage across the 12 ohm resistor, and then we also need to find out what is IX. So that is what we need to solve for. Calculate V, calculate IX. Now here we want to apply, see if we can apply Ohm's law. If you just look at Ohm's law, we can't use anything here yet. Again, we have a scenario where if we want to know what the voltage is across a resistor, so we could say, all right, do we know what the current is through that resistor? No, we don't. There's no current information, so we can't use Ohm's law in this case. That's not going to work. So we can't simplify the circuit because these two circuit elements sitting over here, we don't know what resistor values they are, so we have no idea what to do with them, so we can't combine them. And then we've got this current controlled voltage source over there, which we also can't simplify the source, so that's not going to work either. So now we're going to resort to see if we can use Kirchhoff's voltage law and Kirchhoff's current laws perhaps. So if we take this loop, this mesh, because it's just one, it's a loop inside, there's no other loops inside of it. I've got the 10 volts, that's known. The voltage is the one that I don't know. And then I've got a 4 volts here that I do know. So I can write down for loop number 1, we can actually write down the equation that we're looking for. So let's write down, actually let's write it down like this. I'm just going to erase this one. There's a better way just to, in terms of format. So we're going to write down Kirchhoff's voltage loop law for loop number 1. So we're going into the negative terminal of the 10 volts. Then we're going to the positive terminal of V, and then it goes into the positive terminal of the 4 volts. That closes the loop, so this must equal 0. So what do we have then? Then we know that V equals 10 minus 4 equals 6 volts. Right. So that one's solved. So now we know what V is. Next we need to solve for Ix. Now this is a little bit hidden because initially you would think that you need to solve for a current. It's a current that we're looking for, so do we then need to use Kirchhoff's current law? Well, we don't know what the current is into this node. We know what the current is from there, so that's not going to work. But if we look at loop number 2, what do we have then? We've got a voltage source over here, but we don't know what the voltage is, but we do know the 16 volts, and we do know the 4 volts. So even with loop number 2, we can actually solve for what this, let's call it Vx, what Vx is. So let's write down Kirchhoff's voltage law for loop number 2, and it's going to read, let's start at the 4 volts. So now we're going to the negative terminal of the 4 volts, so it's minus 4 volts. Then we go into the positive terminal of the 16 volts, and then we're going into the positive terminal of Vx. But what is Vx? Well, let's just write Vx is, let's just write down Vx for now, must equal 0, because that closes the loop. So what is Vx? Vx we know is actually 3Ix. Then must equal the 4 minus 16, which gives me minus 12 volts, which means that Ix is then actually minus 4 amperes. And Bob's your uncle. Now we know what the amperes is. So Ix is actually a negative value in this case. Right, that solves example number 4.